Hey everyone, welcome back to the channel. Today we aren't just looking at code, we are looking at survival. We're going to dissect how giants like Netflix, LinkedIn, and Zalando survived their own massive growth. We are going to talk about engineering at the edge. If you've ever wondered how Netflix streams 4K without buffering, or how LinkedIn handles 1 trillion messages a day, this is the blueprint. First, let's look at the menu. We often treat architecture like a religion, but really, it's just a choice of tools. You've got client-server, the classic librarian fetching books, space-based for high scalability, microkernel for plugins. But today, we need to talk about the one that starts it all, and the one that breaks it all. The monolith, the big ball of mud. Most of us start here, the monolith. Ideally, it's a beautiful, solid column. Everything, UI, business logic, data, is in one code base. The good thing is that it's great for startups. It's simple to develop and deploy initially. However, it does come with a con in that it has a single point of failure. Let's dive into a real-world story now. Look at Netflix in 2008. They weren't streaming yet. They were shipping DVDs. A single database corruption caused a 3-day service outage. Because of one error, they couldn't ship a single DVD. That was their existential threat moment. They realized vertical scaling had hit a wall. So, how do you fix a monolith? You break it. Think of a commercial kitchen. In a monolith, one chef does prep, cooking, and plating. If he gets sick, the restaurant closes. In microservices, we split those jobs. You have a prep station, a cook station, and a plating station. Netflix decomposed their application into over 1,000 services. The benefit? If the prep station is slow, you can hire more prep chefs without disturbing the cooks. Independent scaling. The catch is that now you need a manager to coordinate them. That's where things like Zool, which is an API gateway, and Eureka, which enables service discovery, come in. But wait, if service A calls service B and service B is down, we still have a crash. We need to decouple them even further. Enter event-driven architecture. Instead of asking for a response, we just stream events. LinkedIn calls this their circulatory system. They handle 1 trillion messages a day. The concept? Producers, like user clicks, push data into a stream, Apache Kafka. The magic? The producer doesn't care who is listening. You can add a new consumer, like fraud detection, and the producer doesn't even know. You plug it in, and it drinks from the stream. Here is a specific problem Zalando faced. When you have complex logic to calculate a price, and millions of users asking for that price, doing the math on every single click creates massive lag, up to 30 minutes during Cyber Week. The solution? Split the read and write responsibilities. Write side ensures that merchants update prices slowly and handle complex logic. Pre-calculation engine does the heavy math beforehand. Read side ensures the user hits a highly optimized storage. And the result? Latency is dropped to single-digit milliseconds. Now, when you have that much data, you can't just store it all. You need to filter it live. LinkedIn migrated to Apache Flink to do stateful joins on the fly. By filtering and optimizing the stream before it hit their database, they saved 80% on hardware. Walmart uses this for lag-based assignment. If a consumer gets backed up, high lag, the system automatically reroutes to drain the bottleneck. It's essentially traffic control for data. Now, for my favorite pattern, the circuit breaker. In your house, if you plug in too many heaters, the fuse blows to save the house from burning down. In software, we use tools like Hystrix. If the recommendation service fails, the circuit opens. Instead of crashing the whole app, we just show the user a default list of movies. Video player survives even if recommendations dies. Netflix actually invented a tool to randomly kill servers in production just to test if these breakers work. That is chaos engineering. How does Netflix play Stranger Things in 4K immediately when you hit play? The public internet is too slow for that. The solution? They built OpenConnect. They physically put hardware inside your ISP's data center. They use predictive caching to preload shows people are likely to watch during off-peak hours. 98% of the content you watch is served from the edge, down the street from your house, not from AWS. So now we are moving from how many servers do I need to how many events am I processing. Serverless, fast, is perfect for spiky traffic. Look at this graph. Blue line is a traditional server. You pay for it even when no one is using it, idle time. Green spikes is serverless, for example, Lambda in AWS. You only pay when code runs. If traffic jumps from 20 requests per second to 200 requests per second, serverless instantly spins up parallel functions. No DevOps needed. I know this all sounds amazing, but here is the reality check. Distributed systems have a cost. Complexity. Tracking a bug across 1,000 services is a nightmare. It's the whisper game on steroids. Consistency. If you use Cassandra, which is great for scale, you might have eventual consistency. You have to accept that data might be out of sync for a few milliseconds. Observability. You can't just tail a log file anymore. You need distributed tracing tools like Zipkin or Jaeger. Before we summarize, we need to open the toolbox. We've talked about the big structural stuff, but sometimes you have a very specific problem that requires a specialized tool. The Blackboard pattern. Imagine you are trying to solve a crime. You have a fingerprint expert, a DNA expert, and a witness. They don't talk to each other, they just pin clues on a shared blackboard. We use this for non-deterministic problems like speech recognition, where the solution emerges from combined clues. The microkernel pattern. You use this every single day. Think of your Chrome browser or IDE. The core is tiny and stable. Everything else, your themes, your linters, are just interchangeable plugins. This is how you build for extensibility. The broker pattern. Finally, the matchmaker. If you have 50 clients and 50 services, you don't want a messy spiderweb. You put a broker in the middle. It connects buyers and sellers who don't interact directly, completely decoupling them. So, which one do you pick? If you are a startup or building an MVP, then build a monolith. Speed is everything. While you are scaling up and when teams start stepping on each other's toes, move to microservices. As you transform into a global giant, when you hit physical hardware limits, you need event-driven/space-based. As a utility function, use serverless for glue code. Key lesson is that don't copy Netflix unless you have Netflix's problems. As Conway's law states, architecture mirrors organization. To wrap up, here are the 4 rules for the architect. Design for failure. Assume the network will break and the disk will fill up. Decouple everything. Separate compute from storage. Producers from consumers. Optimize for the bottleneck. If you are read-heavy, use caching. If write-heavy, use streams. Automate or die. You cannot manage 1,000 services manually. CI/CD and autoscaling are mandatory. Architecture isn't about finding the perfect solution. It is about choosing the right set of trade-offs. So, I want to leave you with a question for the comments. We talked a lot about scaling up, but we also mentioned over-engineering. Are you currently working on a monolith that's too big to handle, or a microservices system that's too complex to manage? Let me know which of the above 2 are you currently dealing with. If you learned something new in this video, please do consider to like and subscribe for more such Tech Explainer videos. Thanks for watching and see you in the next video.